Okay, this one is 14.4, number 6. And it has us practicing implicit differentiation with these partials. Now in this case, I could probably solve for these directly only because I can solve for this explicitly in terms of z without too much trouble. But let's go ahead and practice this chain rule together with implicit differentiation. Because this function f(x,y,z) is equal to 9, that's a constant. That means the derivative of it will be equal to 0. So that's where I'll start. It's the idea that I've got an f of x, y, and z, and that equals 9. So what that means is the partial of f with respect to any variable, in this case, I'm going to pick x because that's the first one I'm looking for, is going to be 0 because the partial of 9 is equal to 0, and the left and right side have to be the same. Okay, now I can use that fact in order to work out the rest of the problem. So the partial of f with respect to x is equal to 0. And then, now let's take the partial of everything that's inside. So I want to take the partial of fx, and then that's going to be times dx dx. So again, we're applying the chain rule here as if x is a function of itself. Then we'll add to it the same thing. It's the partial y and then dy dx. And that in this case is, well, we'll just write it first. So it's partial of y with respect to x. And then finally, we'll do the last term, and that's going to be partial z times dz dx. And so there we go. That's what I'm modeling right there. And what I want to do now is actually perform each one of these. Well, the first term's easy. Dx dx is just 1. And I know that the partial with respect to x is just going to be, for this term, 4x. So it's 4x times 1 for the first term. Partial with respect to y is 2y, but dy dx, the partial of y with respect to x is 0, because x and y don't depend upon each other. So I know that middle term is going to be 0. But z depends on x and y, so I'll add on to that the partial with respect to z. That's going to be 2z. And then we've got the partial of z with respect to x. And of course, all that is still equal to 0. So that's 4x plus 2z partial of z with respect to x. So if I move the 4x to the other side and divide by 2z, then I end up with the partial of z with respect to x is actually equal to negative 2x over z. And that's the correct partial that I was after. Well, we're going to do all the same thing here, except I just want to redo it. So let's store this. So this is partial z with respect to x, and that answer was negative 2x over z. Now we're going to go back and do the whole thing all over again. I don't want to erase this line because all I need to do is replace the denominators. I want to now do it in terms of y because that'll find that one. So partial y still equal to 0. So that'll be the partial f. Now it's dx dy. Now it's dy dy. And now it's dz dy. And now I can evaluate these separately. Just like before, dx dy is going to be 0. So this whole term is going to be 0. I don't have to worry about it. But dy dy is 1, and the partial of y is going to be 2y. So it's 2y times 1. And then the partial of z is still 2z and dz dy. And that's still equal to 0. So once again, I bring the 2y over, I divide by the 2z, it's going to be negative y over z. So the partial of z with respect to y is going to be negative y over z. And there it is. There are the two partials, and I didn't even have to explicitly solve for z to do it. But if you did, these are exactly the answers you would get. There'd be no difference if you did this as an explicit derivative as opposed to an implicit.